You do really have to know what parameterization is in this class, even if it's rather new as a concept to you. Please dig into this. Each coordinate, whether it's x and y or in 3 dimensions, x, y, and z, has its own function of t. And one function of t defines the x coordinate with respect to time, and another function of t describes the y coordinate with respect to time. This can model the path that a bug travels. The shape of the path does not have to pass the vertical line test. The path can even completely revisit the same point more than once. Why talk about parameterization? Well, it's because some paths that are traveled by bug or by an atom or whatever need more than one function. Sometimes what you have in terms of travel can't just be defining where the y coordinate is in terms of the x coordinate, that's it. So sometimes the movement is more erratic and we need to keep track of this. What really is going to happen is in the final chapter of this calculus class, we will see parameterizations using 2 parameters, a t and then another letter like u, instead of just one called t. So what we're doing now needs to really be fully understood. Now, we're going to switch gears a little bit, talk about polar coordinates. You're most familiar with what are called the rectangular or Cartesian coordinates, x and y. You know, x tells you about how far to go left and right, and y tells you about how far to go up and down. But polar coordinates describe a point differently. You have an r and a theta. By convention, we write r first, then theta next. But I like to think about the theta first. The theta tells you about the angle in the same sense as the unit circle tells you about angle. And then the r coordinate tells you how far to travel along a ray. Now, the r value can be negative, in which case you just travel in the opposite direction. So from one thing before we really dig into this, I should just comment that if you start with the rectangular coordinates, like 3, 7, if you change either the 3 or the 7, you get a different point, right? So 3, 7 and 2, 7 describe different points. And then going back to the 3, 7 we had, 3, 7 and 3, 8 describe different points. However, the same point can be described different ways using polar coordinates, and it happens to be in part due to the periodicity of the angle. So for instance, 6, 0, right here, recall the angle here is theta is 0. Then the next set of polar coordinates, 6, 2 pi. Well, 2 pi, it's technically a different angle, but geometrically gets you to the same location. And then in polar coordinates, 6, 4 pi, they all describe the same point. Actually, for that matter, if you traveled pi radians, that's just half the circle away, but then you traveled not in towards the left, but in the negative direction, so that'd be back towards the right, you actually describe the same point again. So 1, 2, 3, 4 ways shown here to describe the same point. We're going to talk a little bit about converting back and forth between rectangular and polar coordinates. So here's a diagram that I think is helpful to see what's going on. There's a right triangle here. And you can see from this that, let's see, you've got, you know, this side of the triangle is x, and then this value is y over here. So we'll see, you know, cosine of theta is equal to x over r. If you solve for x, you have x equals r cosine theta. Similarly, you'll get y is equal to r sine theta. And those are the formulas, by the way, which are most convenient if you know r and theta, but you need to get x and y, right? If r and theta are given to you, you just substitute here, and then you get the value of x. How about in reverse? Well, actually, because of the right triangle Pythagorean theorem, x squared plus y squared equals r squared, and then you also have tangent of theta is equal to y over x. It turns out that if you were given x and y values, these two formulas tend to be the most convenient for getting r and theta. And there are multiple sets of solutions that work, and we'll see what we mean by that in just a second. So, for instance, what about if you're given in polar coordinates r is 8 and theta is pi over 3? What is this in rectangular coordinates? Well, x is 8 times cosine of pi over 3, which ends up being 4. Y is 8 times sine of pi over 3, which ends up being 4 root 3. If we need to write the point 3, x equals 3, y equals 4 in polar coordinates, from r squared is equal to 3 squared plus 4 squared, you get r is equal to plus or minus 5. And from tangent of theta is equal to 4/3, there's actually many possible angles that you take tangent of to get 4/3, because tangent has a periodicity of pi. But one possible angle, the most convenient angle, comes from arctangent of 4/3. So that could be theta, for instance. Just to point out that there's many possible answers. In polar coordinates, the point that we saw earlier in rectangular coordinates, 3, 4, could be written as 5, arctangent of 4/3. It could be written as 5, 2 pi plus arctangent of 4/3. It could be written as don't travel the full circle, but travel a half circle with a pi here. But then you'll have to go in the negative direction. So -5 for r, comma, pi plus arctangent of 4/3.